exam on Tuesday. Okay. Okay, so 3.9 is related rates. Okay, so if a function, okay, has multiple variables changing with respect to time, and I'm going to put in parentheses or a or an alternative independent variable. But normally it's time that is the independent variable because you can't really manipulate time. Okay, independent variable. It's not always the case, but for the most case, and in this class, the independent variable is going to be time. Okay, everything will depend on time. Okay, if this is true, then we use the chain rule. Okay, dy dt, right? dy with respect to t is equal to dy dx, okay, the regular derivative, but times dx dt. Okay, so this tells me take the derivative with respect to y, or with respect to x, and then take the derivative with respect to t. Okay, so it's the chain rule. Well, the idea here is this, we could write it like this, is that if we had, say, y of x of t, right, y of x of t, meaning that x is a function of t, okay, you could think of it as, we'll take the derivative, you know, take this thing with respect to x, take y prime of x of t times x prime of t. That's really what this is saying. These two are equivalent statements. Just saying, look, if you have a function that is defined for t, okay, but t is not in the function. T doesn't have to be in the function, okay? It doesn't have to be there, okay? For example, if we had, say, y equals x cubed, right? And we wanted to say, and this was changing with respect to time, okay, and this was changing with respect to time. Say that this was a particle, okay, on this trajectory, and we want to know at a specific point in time, okay, whether it's t equals 1, t equals 2, t equals 3, okay, where is that particle located on this curve? Okay, at a specific point in time. So we're not going to take the derivative specifically with respect to x, we're going to take the derivative with respect to t. So what would this become? Well, this y would become dy dt. Okay, it's the derivative of y with respect to t is equal to the derivative with respect to x, okay, so that's 3x squared, times the derivative of x with respect to t. Well, that's dx dt, okay? So very similar to what we've done with implicit differentiation, right? Because when we implicitly differentiated, we have to say, oh, okay, well, this is, you know, this is when we did a y squared or something like that, that would be a y, right? Y with respect to x, right? So then we say, oh, well, this becomes, you know, 2y prime. Well, why do we have to put the y prime? Because that's dy dx. That's the implicit differentiation with respect to x. okay? So, so that's the idea here, okay? So we get things that look like this when we introduce a third variable or an independent variable, okay, that everything is changing with respect to. Okay, clear as mud, right? Let's do an example here. Okay. Okay. So number one, say I throw a rock into a lake. How fast is the area increasing of the wave created, okay, when the radius is increasing at 2 meters per second, okay, 2 meters per second, when, okay, when the radius is increasing 2 meters per second, or I should say and the rate, or sorry, let's not do and. Let's do at the point in time when, or where, at the point in time, no, I can do when the radius is 5 meters. Okay, so let's draw a picture. Okay, say I throw a rock into a lake. Okay, period. How fast is the area increasing of the wave created when the radius is increasing at 2 meters per second? Okay, so big rock, big splash. And what's going to happen to this big rock and big splash? It's going to create a wave. And that wave is going to travel outward in concentric circles. Okay. And we're saying that when the radius is 5 meters, how fast is the area increasing, right? Well, what's the area of a circle? Well, the area of a circle is pi r squared, right? Now, if I wanted to just find, you know, if I just wanted to find how fast the area is changing with respect to the radius, then that's fine. I would just do a simple derivative, okay? I'd be like, oh yeah, a prime is equal to 2 pi r, right? Boom, done. However, we're not asking how is this changing with respect to the radius, we're asking how is this changing with respect to time. So that kind of throws a monkey wrench into it, okay? So this is if change is solely based on radius. Okay, so how is this going to change? Well, this is going to change to dA dt is equal to, we're still going to take the derivative of this thing. Okay, it will be is equal to dA dr, take the derivative of a with respect to r, times dr dt. Okay, that's the chain rule there. So dA dt is equal to dA dr, okay, times dr dt. So look, it will look very similar to this, except for one extra thing. Well, what is this? This above is dA dr. This is dA dr. That's the derivative with respect to r, right? this is changing not with respect to r, change with respect to time. This is changing with respect to time. We have these snapshots in time. Think of these rings as if I took a picture at t equals, say, 0, or this is t equals 0, and then we said, oh, well, after 1 second, it's there. After 2 seconds, it's there. After 3 seconds, it's there. Right? So snapshot at 1 second, snapshot at 2 seconds, snapshot at 3 seconds. Okay, and the area is growing at a certain rate with respect to how fast the radius is growing. Well, how fast is the radius growing? Well, the radius is growing at 2 meters per second. Well, that's dr dt. dr dt is how fast the radius is growing. That's 2 meters every 1 second. Okay, 2 meters per second. That's how fast this thing is growing. Okay, and so how do we reconcile this? Well, how fast is the area growing? Well, that's dA dt is equal to dA dr. Well, what was dA dr? Well, that was above here. That was 2 pi r. 2 pi r, and then dr dt. Okay, let's plug in what we know and solve for what we don't know. Okay, so this is going to be dA dt is equal to 2 pi r. Well, what's the radius? What's the radius at the snapshot in time that I'm looking at? 2 meters? No. Let's go back to the question. What does it say? It says at the point in time when the radius is 5 meters. So we're taking the picture, click, when the radius is 5 meters. Does that make sense? Okay, good. Okay, thank you, Giselle. Okay, yeah, so when it's 5 meters, we're taking that snapshot. Okay, and so there I'm just gonna plug a 5 in here, and then how fast is the radius growing? What's that dr dt? That dr dt is the 2 meters per second. This is 2, so this is gonna be 5 meters, okay? And then this is 2 meters per second. Okay. So now if I multiply this all together, I get 20 pi. This is dA dt. This is going to be 20 pi meters squared per second. Now, does that make sense? Does the units make sense here? That it would be meters squared per second. Well, yeah, because what is dA? dA is the area, and what do we measure area in? Square units, right? So this is square units. That's cool. Okay, that makes sense. And then what's dt? Well, that's measured in time. So we've got square units over time, meters squared over seconds. Meters was what they gave me. So the area is growing at 20 pi meters squared per second when r is equal to 5. When I have this wave moving from the center, I'm going to put a little arrow here. That's a vector. Okay, you don't need to know what that is. But this is moving outward at a speed of 2 meters per second. And what's how far away am I? I'm 5 meters, right? Then what's the area doing? The area is growing the area at 20 times pi. Well, that's 6.28 is pi, 2 pi. So this is going to be 62.8, or roughly 63. Okay, this is going to be roughly 63 square meters per second. So the area is not 63 meters per second. That's not the area when r is equal to 5. If I want to find out what the area was when r is equal to 5, I can just plug it into that's the easy way. Just go 5 squared, okay? So I want to know how fast is this growing, okay, every second. Well, this is growing at 63 square meters every second. So in the next second, it should be growing 63 square meters, okay? as opposed to the area, which is this thing, which, you know, if it wasn't changing, if it was just all we wanted to do is find the area at 5, we wouldn't have to do any calculus. But because it's changing with time, we have to use the calculus, and that's what calculus is really good for. Okay, it's to help us deal with stuff that's changing. Okay, and since we deal with the real world and time is always moving, we have to deal with things that change with respect to time. And so this is how much it's growing. It's growing at 63 meters per second. Now, what would be the area? The area would be, I don't know, what's 25 times pi? 25 times a pi, okay, is 78.454. Okay, I'll just say 78.5. Okay, so this is 78.5 meters squared, growing. It's almost going to double in the next second. Okay, growing at 63 meters squared per second when r is equal to 5. Okay, so it will almost double in the next second. Okay, when r is equal to 5. Okay, how many seconds until r is equal to 5? Well, if this thing grows 2 meters per second, we'll do times x, or times t, I guess. Times t is equal to 5 meters. Well, divide by 2. Okay, and we get t is equal to 2.5 seconds. So after 2.5 seconds, I will throw that rock in. After 2.5 seconds, I will have an area of 78.5 square meters, but it will be growing at 63 in the next second, within the next second, after 2.5 seconds to 3.5 seconds, the area will have grown 63. It will almost double in the next second. Okay, so in my original drawing, I really should have had this maybe at 2 and then 2.5. Okay, because after 2.5 seconds, we will have hit the 5 meter mark, right? So let's go back. Let's just try to get rid of just that 5. There we go. 2.5. This whole thing is 5 meters. Okay, and this is 2.5 seconds. Okay. Okay. Now, how does this deal? How does this apply to your life? Because you're like, oh well, I'm not often by a lake throwing rocks in. And you're like, okay, that's fine. Well, you're right. We don't need to be throwing rocks in lakes, but I want you to understand that this is how we calculate. We have to use implicit differentiation to do this. Okay, implicit differentiation. Okay, so let's do one from business here. Okay, the total revenue and cost for repairs on X houses are given by R of X is equal to 1,000x minus x squared, and C of X is equal to 3,000 plus 2x. Okay, we've got revenue and cost. Okay, so suppose the company can or let's say is adding 10 homes per day. Suppose the company is adding 10 homes per day. They're increasing the number of homes by 10 every day. I don't know how long they can sustain that, but it's all good. Okay. Suppose the company is adding 10 homes per day at the moment when the 400th customer is signed. Okay, so the moment that they've signed 400 customers. Okay, so what is the rate of change of the profit with respect to time? What is the rate of change with respect to time? Not the rate of change with respect to the homes, but the rate of change with respect to time. Okay. So here's the deal. We know that that the number of homes is equal to X. How fast is X changing with respect to time? Well, that's dx dt. That's how fast is how fast is this thing growing? And it's growing at a constant rate of 10. Okay, this is how fast the number of homes being added daily is increasing. Okay, it's increasing by 10. Okay, so that's dx dt. Okay, so we want to find out how fast is the profit changing. Okay, so profit P of X is equal to R of X minus C of X. Right? Okay, so what was R of X? R of X was 1,000 minus, or 1,000x minus x squared. C of X was 3,000 minus, oh, should this be 20? I think it should be 20. Yeah, it should be 20. I messed up. This should be 20, not 2. There we go. That will help. That will help. Minus 20x. Okay, so that's the cost. 3,000 minus 20. Okay, 20 times x. So x is the number of homes. Okay, and okay. And again, I screwed up. This is plus. Okay, I think we're good now. But I can just write things down properly. Okay. Okay, 20x. Boom. Okay. So now let's distribute and simplify. P of X is equal to, okay, 1,000x minus x squared minus 3,000 minus 20x. Okay, so 1,000 minus 20x, that's 980x minus x squared minus 3,000, okay, is P of X. Okay, so now what are we taking the derivative with respect to? We're taking the derivative with respect to time. So this is dp dt. Okay, since we only have one p. Now, dp dt, right? And then what would the derivative of 980x be? Well, it would be 9a, but you have to think implicitly. What happened when we took the derivative of y with respect to x? We had to have a y prime. The same thing is true here. You have to have an x prime. Okay, think of the x is not the variable that we're taking the derivative on. We're taking the derivative with respect to t, not x. So we have to implicitly differentiate. So this is going to be 980 times dx dt. Okay, minus this guy here. Take the implicit differential of this, and this is going to be 2x dx dt. Okay. So we have dp dt. Okay. Another way to think about this, and this 3,000 just goes to 0, right? Another way to think about this, we'll pause here and do a little aside. Okay, so a little pause. Okay, this is like a parenthetical thought. Okay, we can also think of this as P of x of t is equal to 980 x of t. Maybe writing it like this will make you think of, oh, that's right, we've got to take the chain rule here, minus x of t squared minus 3,000. You can think of it either way. So if I were to take the derivative here, p prime of x of t, well, that's going to be 980. Okay, 980. Derivative of 980x is just 980, but what's the derivative of x of t? That's x prime of t. That's my dx dt. Okay, minus, what's the derivative of this thing? Think chain rule. It's the derivative of the outside, 2 times x of t, times the derivative of the inside. Well, what's the derivative of the inside? Well, that's x prime of t. And again, the derivative of 3,000 is 0, and so that just goes to 0. Okay, so again, either notation, you can use either notation here. Okay, so I'm going to go back to the dp dt notation. Okay, dp dt is equal to, okay, 980 dx dt minus 2x dx dt. Okay, so now, how fast, what's dx dt? How fast is the number of homes growing? What is dx dt? Any ideas? $10. Good. Thank you, Oscar. 980 times 10 minus 2 times x, we'll talk about x in a minute, times dx dt, which is 10. Okay. Okay, what's x? How many homes have been worked on? Okay. Well, it's 400. 400. Have you read the problem? Okay, so we have dp dt is equal to 980 times 10, that's 9,800, minus, this thing is 2 times 400, that's 800 times 10, that's 8,000. Okay, and so the dp dt is equal to 1,800. Okay, 1,800 what? Well, what is P? What does P represent? Maybe you forgot already. Any ideas? What does P represent? Oh, what do we have up here? Okay, R of X and C of X. Oh, okay. So yeah, P was profit, right? What do we measure profit in? Any ideas? What do we measure profit in? Dollars. There you go. Dollars, monies. Okay, monies. And then what are we measuring time in? What are we measuring the time in this problem? Days, exactly, dollars per day. So what is this saying? This is saying that the profit is increasing, because it's a positive number, at $1,800 per day when the 400th house is signed up for repairs. Okay, so at the time that we're going up 10 houses a day, we're also going up $1,800 per day, or approximately $180 per house. Okay. Okay, let's do one last example here. Okay. Okay, so the cost of tile is, say, I don't know, let's do $15 per square foot. Okay. Okay. So what do I want to do here? So given a circle of x squared plus y squared equals 100. Okay, x squared plus y squared equals 100. Okay. And a tile can be laid at a rate of 20 square feet per hour. Okay. Calculated 20 square feet per hour. Let me think. What I want to do here. Quick. No, I like that. And then calculate at a rate of 20 square feet per hour. Okay, find the rate of change in y given a rate of change in x. Okay. Of rate of change in x of we'll just say that it's of the 20 square feet, or we'll just say 20 feet 20 feet per hour. Okay, given a rate of change in x of 20 feet, no, not square feet, okay, per hour. Okay. Yeah, so let's see what we can do here. Okay. Okay, so we're going to have to take x and y, okay, equals to 100. And we're going to have to implicitly differentiate this on, not on x, on y. I'm sorry, on t, okay, per hour. So this is going to be 2x dx dt, implicitly differentiate that on t, okay, plus 2y dy dt, okay, is equal to 0. Okay. Okay. Nice, nice, nice. Okay. Okay, so the idea here is that we have 2x dx dt, okay, plus 2y dy dt, okay, is equal to 0. But I'm going to toss 1 to the other side and make it negative. I'm going to take this and toss it to the other side. Okay, because I want to find the rate of change in y. I want to solve for dy dt. Okay, so what is dy dt going to be? Well, I could divide by negative 2y. And I'm going to get dy dt is equal to 2. The 2's are going to cancel. This is negative x over y dx dt. Okay. Okay. And so I need to figure out, well, okay, what is x, what's y, and what's dx dt? So I'm going to include one piece of information. I want to know at what point in x, okay, how far in x okay, how far, at what point is the snapshot? Okay, we know that it's changing at a rate of 20 feet per hour. The x is changing at a rate of 20 feet per hour. Okay, but we want to know how fast is the y changing? Okay, so this 20 feet per hour, what is that? That's my dx dt. That's 20 feet per hour. But I want to know how fast is the y changing when, okay, and I'm just going to put this in here, when x is equal to 10. Okay, so when x is equal to 10, okay, well, maybe not 10. Let's not do 10. Let's do when x is equal to 6 feet. Okay, when x is equal to 6 feet. Okay, how fast is this thing changing? When x is equal to 6 feet. Okay, so what we have to do is we have to go back to the original. You see how this has a x, a y, and a dx dt. Well, we already know what the dx dt is. That's one of the pieces of information we know. We also know what x is. Okay, I just gave you what x was. Okay, I said when x is 6 feet, okay, dx dt is 20 feet per hour, and that's number 2. And what I need to figure out is I need to figure out, well, what's y? Well, how can I figure out, well, what y is given x? Any ideas? How can I figure out what y is given x? Well, is there anything that relates x to y? Well, yeah, how about this right here? Doesn't this relate x to y? Don't we have x squared plus y squared equals 100? Right? So we have 6 squared plus y squared equals 100. This is 36 plus y squared equals 100. Subtract 36. y squared equals 64, so y is equal to 8. Oh, okay, so y equals 8 feet. Okay, so now we have all three pieces of information that we need to solve for dy dt. We have dy dt is equal to, okay, negative, okay, 6 over 8 times dx dt, which is 20. Okay, so dy dt, okay, so as the x is going up, the y would have to be going down. Okay, and so dy dt, this is going to be 120 over 8. What is that? 120 divided by 8 is 15. So this is negative 15, okay, feet per hour. Okay, so the y is going down in this case. Okay, so, and I'll just stop there. We won't go into the pricing formula for this. Okay, but we could see how is this thing changing. Okay, if we have a circle of radius 10, right? Okay, we're always on the outside of this thing. Okay, and then we say, oh, well, the x is 6 and y is 8. Okay, so 6, 8, and 10, that's the radius there. That's the snapshot in time that I'm looking at. And we would say, well, how fast is this thing? How fast is the x growing? Well, the x is growing at 20 feet per hour. Okay, and then how fast would the y be growing? Well, the y would be shrinking. Okay, so the y would be going, the x would be going out. Okay, the x would kind of be like we're going this direction. Okay, the x would be going out, but the y would be going down. Okay, as the x increases, the y decreases. So that's why this is a negative amount if we're on this, if we're restricted to that circle. Okay, so as the x's go over, the y's go down. As the x's go negative, the y's go up. Okay. Okay, well, that's it. I mean, I'm going to stop there for today. That's all of chapter 3. It's a pretty short lecture today. And that's it. Yeah, it's just one section, 3.9. That was the end of chapter 3. So we'll review on Thursday, and then